listening to the Futures Podcast with me, Luke Robert Mason. On this episode, I speak to theoretical physicist Jim Al-Khalili.
But ultimately, there's a reality out there. And for me, science and physics in particular is the best way of understanding the nature of that reality.
Jim shared his thoughts on what theoretical physics can teach us about the nature of reality and the mysteries of our universe, the possibility of a theory of everything, and how to make scientific ideas accessible and captivating. This episode is an edited version of a recent live stream event. You can view the full unedited video of this conversation at futurespodcast.net. Now, theoretical physics has become our most useful tool in understanding the origin of space and the meaning of time. It has been so effective that the late Professor Stephen Hawking claimed that physics might soon provide us with a theory of everything. But new discoveries like quantum mechanics and dark energy, combined with the challenge of unifying all of these concepts, are forcing physicists to confront captivating new unknowns. In his beautiful new book, The World According to Physics, Jim Al-Khalili explores just how far physics has gone in demystifying the world, and then outlines how far it still has to go in teaching us about the nature of reality and the weirdness of our universe. So, Jim, there is so much that I want to ask you, but from reading the book, it is abundantly clear that you have a perhaps inappropriate love affair with physics. So I guess I want to know, what is it about the field of physics that makes it such a captivating way to understand our reality?
Well, you know, I sometimes am puzzled why everyone isn't completely in love with physics, because it deals with the deepest questions. I remember when I was growing up as a kid, wanting to know, does space go on forever? What are stars made of? What do atoms look like? What is time? The big questions that we all sort of, about of reality that we ask. And at some point, I must have been about 12, 13 or 14, I realized that physics was the subject that tries to answer those questions. And that was it for me. So, okay, it helps that I'm good at maths. It helps that I like solving puzzles and solving mysteries. But physics was really sort of basically common sense about how the world worked. But it gave me the tools to ask some of these really deep questions. And that's what I've done all my life. And I still keep asking those same questions.
Now, science and rational inquiry, which underlies physics, it's done so much to demystify our world. Do you think that's necessarily a good thing, or is some mystery actually quite useful?
Well, I think it would be a boring world if we had all the answers. That absolutely, there's no doubt about that. It's a bit like the anticipation of opening your Christmas presents on Christmas morning. There's that excitement of not knowing what you've got as a kid. I mean, maybe not so much for me now. I know it's socks and aftershave. But once you've opened your presents, yes, you've got your new toys and whatever that are there, but the mystery's gone. Somehow the magic has disappeared. And I think it's the same with trying to understand the universe and our place in the universe. The mystery about it is wonderful. And I think a lot of people have this misconception that science is about certainly demystifying, because mysteries are there to be solved. But somehow, we want for there not to be mysteries. We want for the world just to be rationally explained away, without any puzzles, without any magic, without any wonder. And that's simply not the case. There are still so many mysteries out there, so many things we have yet to understand. So yes, physics demystifies, but it also shows us new mysteries that we have to tackle and new challenges.
I mean, one thing that science and physics does really well is show us a version of reality. And in some cases, in the case of physics, it shows us a singular objective reality that can be understood through science. And do you think there's such a thing as a singular objective reality? Do you think physical theories could really be able to be used to approximate the truth of physical reality?
I do, yes, but that's not to say that all physicists or philosophers of science agree with me on this. My view is that there's a world out there, there's a universe, a reality out there. It's been in existence long before humans came about and started asking questions about it. And the role of science and the role of physics is, as you say, to approximate as closely as we can to that objective reality, the truth of the way things are. And there aren't different realities or different truths. It's not that you arrive at a different. There are different ways of explaining. Different ideologies, religions, philosophies, but ultimately there's a reality out there. And for me, science and physics in particular is the best way of understanding the nature of that reality.
Where have we seen examples of physics helping us to understand that physical reality? Physics theories helping us understand that physical reality?
The way physics has developed for many, many centuries. An example I use in the book is that if I were to drop a ball from a height of 5 meters, physics tells me that it will hit the ground in 1 second. Right? There's a simple formula actually developed by Galileo, right, even before Isaac Newton, that tells you drop it from 5 meters on Earth. The pull of Earth's gravity will mean it falls and hits the ground in 1 second, not half a second, not 2 seconds. No ideology, no amount of meditation or prayer, no philosophy, nothing will tell you it'll hit the ground in 1 second other than physics. The universe, described mathematically, which we now explain using physics. So that's a fact, a truth about reality that physics tells us. It doesn't matter how far our theories develop, and Einstein replaced Newton and someone else will replace Einstein, that will always remain true.
When it comes to physics, it's often this thing that's done by, obviously, physicists. And you say in the book that there are 2 types of physicists. Number 1, there's the searchers and the dreamers. And number 2, there's those who play it safe by exploring the theories that can be tested with experimentation. So, Jim, what kind of physicist are you?
Somewhere in between, he says boringly. Yeah, I mean, those 2 categories, I guess they apply more to theoretical physicists rather than experimental physicists. When you study physics at university, if you want to go on to academically to do physics research, you have to make this choice. You either become a theorist or an experimentalist. The theorist does the maths, solves the equations, writes the computer codes, develops the models, the simulations. The experimentalist in the lab carries out experiments to test the way the world really is. But among theorists, there's these 2 types. So the example I use in the book is if you walk along quiet pavement late at night and you almost get home and you realize you've lost your keys through a hole in your pocket. So you go back to retrace your steps to look for your keys. Now, if you look in the pools of light underneath the lampposts, that's where you're most likely to be able to see your keys if they're there. But of course, they're more likely to be in the larger areas of darkness in between the lampposts. So the 2 types of physicists, there's the searchers in the dark who grope around in the dark. They don't know what they might find. They're less likely to find what they're looking for, but the rewards are bigger. And then there are safer physicists who look in the pools of light. They're more likely to make advances, but they'll be incremental advances. They're not likely to sort of create a revolution in physics. So yes, people working on sort of cosmology or string theory, these are the searchers in the dark. They're the adventurers, but they could spend all their lives without coming up with a revolution in physics. But if they do, and there's your Nobel Prize.
But which one is more fun? Is it the prediction game or is it the proof game? I mean, much of physics that was theorized has now been proved, but the ones who did the predicting are the ones, as you just said, who win the Nobel Prize. So which one do you think is more fun?
I think it depends on your personality, as a scientist, because there are physicists who are quite happy to spend their whole career developing a very esoteric mathematical model of what happened, say, before the Big Bang. They almost know there's no way of testing that idea experimentally, but that's fine. They will come up with their elegant mathematical equations, and for them, that's fulfilling enough. There are the other physicists who don't feel a sense of achievement or fulfillment unless they can test their theory against data, against observation experiments. I've spent most of my research career actually developing theoretical models that can be tested against experiment. And for me, that's the success, that if my model prediction matches what people see in the lab, I say, okay, well, my equation explains the way the world actually works. And that's very, very satisfying. But it may not be so exciting.
Well, you do such a good job in this book of making physics exciting, regardless of what sort of physics that it is. And you do such a good job at summarizing many of the key theories in physics, from everything from space and time, energy and matter, quantum mechanics, thermodynamics. But I want to take it one step back and ask you, what was the impact of the telescope and the microscope on human perception? How were these two tools key to our understanding of the world through something like physics?
More than any other instrument in human history, certainly in terms of understanding the world, the telescope and the microscope really revolutionized our view. Because until then, all we could understand about the world is the world that we could see with our senses, with our naked eyes. Once you have a telescope, that brings the very far close to you. So we could study the stars and understand the cosmos. The microscope brings the very small, again, into view and enlarges it. And so we could delve into the microscopic world. Now, of course, as you say, our two most important or powerful theories in the whole of physics are general relativity, Einstein's theory describing the very large, and quantum mechanics, describing the world of the very small. So without the telescope and microscope, those worlds, the very far and the very small, wouldn't have been available to us. And that happened in the 17th century, and suddenly that really kick-started the scientific revolution.
That happened at that time, and also Galileo helped to mathematicize physics. Now, why was that so important to how we think about physics today?
It wasn't obvious that the universe spoke in the language of mathematics. Today we take it for granted that it doesn't matter what part of the world you are as a scientist, what language you speak, you can write down an equation and it describes some aspect of the world, which would be exactly the same equation for anyone else in the world, for any culture in any age. And so there's a universality about the mathematics of the physical universe. Galileo was trying to understand how objects fall, they accelerate in Earth's gravity, but to give a simple algebraic expression which allows us to make predictions, to allow us to do calculations, that really meant that we could develop our theories because they could then mathematically make predictions that you could go and test against an experiment. Rather than just qualitatively saying, well, I suggest that the world looks like this, that the sun orbits the earth, whatever, the ancient Greeks were thinking about. They were very good at philosophizing. But to pin the properties of reality mathematically allowed us to develop our theories much more effectively. And of course, there was no looking back after that.
In many ways, it feels like physics is this process of picking the right model and picking the right mathematics and applying it to the right system. Is that a good way to summarize what physics actually is?
By and large, yes. The system, the phenomena that you want to study, you have to choose the right theory that applies there. It's a matter of scale. It's a matter of the sort of phenomena you want to understand. If you want to understand, I would say, if you want to fix your washing machine, you don't need to know the standard model of particle physics, even though your washing machine is ultimately made of quarks and electrons. You don't need that. You need to understand the mechanics and electrical circuitry. So yes, whatever phenomenon, whatever system you want to understand in the universe, you have to apply the appropriate theory that gives you the best way of learning.
And physics plays in two spaces, really. It feels like it plays in the very, very big of space and time and in the very, very small. But what was so revealing about your book as someone who knows absolutely nothing about physics is that there seems to be some sort of relationship between the two. Could you explain that a little bit more?
Yeah, I mean, these are the two most powerful theories in physics, certainly 20th century physics. Einstein developed his two theories of relativity at the beginning of the 20th century, which we now know describe space and time and the cosmos and the universe at large. Essentially, how gravity, matter and energy have a gravitational field which shapes the structure of the universe. So that's on the very largest scale. And it's a very beautiful, very accurate theory. But it doesn't apply when you zoom down to the tiny microscopic scales. Down there at the level of atoms, we need a completely different theory, quantum mechanics. And quantum mechanics in its own domain is also extremely powerful. Without quantum mechanics, even though it only describes things we can never see with the naked eye, namely atoms and the particles that make them up, without it, we wouldn't be having this conversation, because without quantum mechanics, we wouldn't understand the nature of how material conducts electricity, how semiconductors work. We wouldn't have developed silicon chips, microchips, computers, and essentially almost all of modern electronics relies on our understanding of the quantum world. So it's very powerful, but it doesn't apply, as far as we can deduce at the moment, to the very large. In the same way that general relativity, Einstein's theory of the cosmos, doesn't apply down at the subatomic scale. And that's annoying. You might think, well, why? You've got the world out there perfectly described by a theory, and the world down there very small, perfectly described by a very different theory. Live with it. That's the way it is. But there are instances, there are examples where both theories should apply. They're rather sort of exotic examples. For example, the Big Bang itself, or the singularity at the center of a black hole. But it seems that those two theories are very different and don't mesh together. And so the holy grail of physics, the ambition that so many physicists have, is to find a theory that somehow is an uber theory, that from which emerge both quantum mechanics and general relativity. This is what we call a theory of everything.
Well, it's a theory that unifies everything. And that's really key to this book, or at least it feels like it's a key theme within this book, the idea that there will be a unification of physics. So what is unification? What is this theory of everything? And why is it such a major aim for physics and physicists?
We've discovered ever since modern physics first developed by people like Galileo and Newton, that seemingly disparate and quite independent phenomena ultimately seem to have a connection between them. So Newton started us off. He realized that the reason an apple falls to the ground, whether or not one actually fell on his head on his mother's farm, we don't know. He tells that story. But right, so the reason the apple falls to the ground is due to the same force that keeps the moon in orbit around the Earth and the Earth in orbit around the sun. It's the force of gravity. We learn about it at school now. But back during Newton's time, it wasn't obvious. That the forces controlling earthly objects need not have anything to do with those forces controlling the heavenly bodies. And so there was that unification of forces due to gravity. James Clerk Maxwell, the Scottish physicist in the 19th century, unified electricity and magnetism and showed that they are part of the electromagnetic field, and light is a traveling electromagnetic wave. So again, people didn't realize there was a connection. Throughout the 20th century, we've seen this process of unification actually pick up pace. So quantum mechanics was developed. That was combined with Einstein's special theory of relativity. It was combined with Maxwell's theory of electromagnetism. The forces inside atomic nuclei were explained by quantum mechanics. And you get to the point where you have one all-encompassing theory that describes all the forces down at the subatomic scale, and another all-encompassing theory describing the universe at large. So we sort of expect or hope that there is that next step that brings these two theories together. And we just haven't figured it out yet.
Why is there that hope, though? Why is unification, why is it so necessary for physicists to find something that unifies all of these theories? Does it just satisfy some weird desire that physicists have for things to be mathematically perfect, and they just like theories when they're aesthetically pleasing, or is there something deeper going on?
So it's just so that we can fit an equation on our T-shirts.
100%.
No, it's more than vanity or just a sense of satisfaction. In unifying phenomena and ideas and forces, we develop a deeper understanding. What we arrive at is a theory that gives us a better understanding of the universe than the previous two theories that were not connected. And so in unifying, we're not just simplifying for convenience and just for neatness, but because it helps us reach a deeper truth, that ultimate truth about the nature of reality we spoke about at the beginning. We feel we're getting closer to it. We don't know how how much further we have to go, of course, because it's almost sometimes it feels like peeling back layers of the onion. Oh God, who ordered that? Where did that? What dark matter? Come on, But we do feel we are moving in the right direction. I mean, one example as to why a theory of everything is why we want to unify Einstein's general theory of relativity, the theory of gravity, with quantum mechanics, is that in quantum mechanics, there's this idea that a subatomic particle, say an electron, can be in two places at once, in what we call a superposition, or that it can actually have two energies at the same time, two quite separate energies, in a way that, just saying the words means it's absolutely meaningless. Quantum mechanics is counterintuitive. But if an electron is in two places at once, we also know from relativity that matter causes space-time to curve around it. That's a deep explanation of what the force of gravity is. It's the curvature of space-time. So if an electron is in two places at once, space-time curvature has also been split. So space-time is also in a quantum superposition. So we know that ultimately our theory of space-time, general relativity, must somehow be combined logically with the quantum world, the theory of the quantum world. So we know it's there. We just don't know whether we have to modify quantum mechanics, modify general relativity, or somehow scrap both and start from scratch.
well, you introduce us to two possible contenders for this theory of everything within the book. The first one is string theory, and the second is loop quantum gravity, which sounds like something out of science fiction. What is the difference between the two, and do you think either of these could potentially become that theory of everything?
It's possible. I mean, they've both been going for some time now, and they both have their proponents, their advocates, their cheerleaders, physicists who've spent their careers thinking about them. They're both highly speculative mathematical theories. String theory developed first in the mid-80s and then underwent a second revolution in the mid-90s, suggests that ultimately matter is made of tiny vibrating strings, not point particles. But these are strings vibrating in higher dimensions. So it's very esoteric, very abstract, but it gives us a way of unifying the force of gravity with the other three forces which are already contained within our quantum theories. Loop quantum gravity, on the other hand, isn't about unifying the four forces, but rather how do you quantize, this is the word we use when you make something behave quantum mechanically, how do you quantize space and time? And so either one of them could be right. And, I don't work in either field. I've got good friends and colleagues who work in both. In fact, I recently interviewed Brian Greene, American string theorist, who would argue that string theory is the theory of everything. We just haven't figured out everything about it yet, but it's the correct theory. And then Carlo Rovelli, for example, Italian physicist who's written some wonderful best-selling popular science books. He's an advocate, a fan of loop quantum gravity. And again, he would say, oh, no, the string theorists, they've had their time. They've got nowhere. They've been thinking about this for decades. Loop quantum gravity is much more sensible. So it's almost like different ideologies, different religions, which camp are you in? And in the book, I try and, because I don't work in either field, I can sort of step back and say, well, they've got their good points. They've got their good points. But what we need, of course, is to find a way of testing them. Ultimately, a scientific theory stands or falls based on whether it correctly describes the real physical universe, which means we have to find some way of testing, carrying out an experiment, carrying out an observation that can tell us whether these theories are right or wrong. At the moment, we don't know how to test them. You could almost ask whether they're proper scientific theories. Are they just metaphysics? Are they just philosophy with pretty maths? Because we don't know how we can check whether or not they're right.
Perhaps it's a good thing that we can't check if they're right yet, because if we did achieve that unification, you talk about in the book achieving something else, which is the end of physics. In other words, you can pack up and retire because physics will have achieved what it wanted, that unified theory. What is the end of physics? And could physics actually be in crisis in the 21st century if we find this unified theory?
I think many physicists would argue that if there is a crisis in physics, it's because the end that we thought was in sight isn't. So, if you want more mysteries, if you're thinking about going to physics, as a young budding scientist, then great, because I think the end is further away than we thought. The end of the 19th century, physicists thought that everything was done. We had Newtonian mechanics and its law of gravity. We had Maxwell's electromagnetism. We had thermodynamics, statistical mechanics, all branches of physics that are still good and proper today. But people thought that was all there was to know. And so the end was in sight for physics. And then in the 1890s, we discovered the electron. We discovered X-rays, so-called because, X for the unknown. We didn't know what X-rays were. And we discovered radioactivity. And then, the turn of the 20th century, and then you have the quantum revolution. Einstein comes along. You realize, whoa, you thought it was the end of physics. We're just starting. And we almost thought it was the same. We're getting to the end of physics, the end of the 20th century. Stephen Hawking even wrote a famous paper around about 1980 saying, is the end in sight for theoretical physics? We're getting close to the theory of everything. It looks like we aren't really very close to it all. And other mysteries have popped up since then anyway that we have yet to try and understand.
Well, if I can just be a cheerleader for the 21st century for a moment, we have actually discovered stuff in this century, in 2012 and 2016. Could you tell us about some of those discoveries?
Yes, of course. And what's wonderful is that these are discoveries that have made it out into the wider world. It's not just physicists who will know about it. Everyone heard about the Higgs boson, discovered at the Large Hadron Collider in Geneva in 2012. Peter Higgs and others, the theorists who had predicted the existence of the Higgs boson, this elementary particle, this lump of energy, had predicted it half a century ago. And finally, the experiment confirmed that it really existed, and they got their Nobel Prizes. And then, of course, in 2016, the discovery of gravitational waves. So these were experiments, absolutely remarkable laboratories in America called LIGO. They're two sort of twin laboratories on either side of the states, and they've picked up these very, very tiny, delicate ripples in space itself coming to us from the collision of two black holes. It's a bit like dropping a stone in a pond and then the ripples radially moving outwards. And if the pond's very, very large, you'll just see a tiny ripple at the shoreline. And that's the evidence that a stone was dropped in the middle of the pond. So 2016, gravitational waves. But again, they were predicted by Einstein's theory 100 years ago. So yes, these were absolutely incredible experimental results and got the world of science and beyond all very excited. But they were predicted already. We would have been much more surprised if we hadn't found the Higgs boson and we hadn't found gravitational waves. Having discovered them, they're we've ticked the box, right? Good. Yep. Okay. So Peter Higgs was right. Yep. Einstein was right. What now?
Well, you almost reveal in the book, and you struggle to say it, but perhaps it would have been better for science if we hadn't found the Higgs boson, because it would have challenged the standard model of physics, and that could have actually been quite a positive thing.
I think had it been confirmed not to exist, the standard model of particle physics, as it's known, would have had to be not ditched, but revised and rethought. It will be back to the drawing boards. And that's what we want. We want to prove theories wrong and replace them with new ones, because there's the excitement, there's the mystery, there's the Nobel Prizes all around. You don't want to confirm that some guy 100 years ago was right all along. Where's the fun in that?
I mean, the one problem that would have caused is the public perception of science, especially publicly funding very expensive sort of science, would have been in real crisis if they'd turned the thing on and actually found nothing.
Found nothing. Yeah, no, absolutely. And we do really have to work hard, and we're seeing this now during the coronavirus pandemic. Need to work hard at explaining to wider public, wider society, how science works, that it's okay to make mistakes or to be wrong or to make a wrong prediction, because when you gather more evidence or you carry out a new experiment, you learn something new and you can revise your picture of the world. To some extent, the Large Hadron Collider actually has been suffering from this point that you make about whether or not it was all worthwhile, because I think so, for a lot of people, once the Higgs boson was discovered, they said, right, okay, so you found it. So you're all just going to shut up shop now and all go home? And they say, oh, no, no, no. The Large Hadron Collider is, we want to discover lots of other things. We want to discover if there's evidence of other new types of particles out there. But that wasn't solved. The Higgs boson was the poster child of the Large Hadron Collider. But of course, what has happened is that we haven't discovered anything since then. Since 2012, 8 years later, experiments have been running, and we've not discovered any other new particles. So there might be the accusation that it's a very, very expensive machine that has been built to confirm something that we sort of thought probably existed all along. But then, unless you're curious, unless you take the plunge and you try and do what you can to unravel the secrets of the universe, then, well, I think that defines our humanity. It's there, like Mount Everest. You have to climb it.
In many ways, it's turned into just a very expensive cycle path. It looks fun when those people are cycling through that thing.
Maybe.
As I read the book and as I listen to you now, it feels like physics is like trying to empty your email inbox. When I'm trying to empty my email inbox, the only way I can get to inbox zero is to reply to all my emails. But when I reply to all my emails, that leads to more inbound emails. And in the same way, the more answers that you get from physics, the more questions you seem to have. So why is that?
Why even bother? We think we're approaching that ultimate reality. We didn't understand the nature of matter. We discovered that normal matter is made of atoms. Then we look inside atoms, we realize they're made of atomic nuclei with electrons buzzing around the outside. Then the nucleus is made of protons and neutrons. Protons and neutrons are made of quarks and gluons. Other quarks and gluons really vibrating strings. So in a sense, you think, well, are we going to keep going forever? But at the same time, I think there's good reason to believe that mathematics is pointing to, there should be an end in sight. We haven't discovered a fifth force, for example. We know there are 4 fundamental forces in the universe. We haven't discovered a fifth. Now, there may be a fifth one, but we're getting closer to taming and understanding, unifying the 4 forces of nature. So it may be that physics will come to an end one day. It may be that we will get so close to the ultimate understanding of the ultimate nature of reality, there won't be many more revolutions or paradigm shifts or big changes in our worldview. But I think we're a long way off from that at the moment.
I mean, when looking at the entire history of physics, what personally is more dazzling to you? Is it the success of fundamental physics to this date, or the questions we still have yet to answer?
That's an interesting question. I mean, I'm fascinated by the history of science and the history of physics, and I love reading the biographies of some of the great heroes of mine, the big names: Niels Bohr, Richard Feynman, Einstein, Paul Dirac, and so on. And I get a sort of a tingle, a sense of following in their footsteps, and how they came to understand what they saw. So for me, there is a romance about the adventure of the journey that physics has taken thus far. But then in my day-to-day life, in my research, and I've just spent this afternoon several hours talking to a couple of my PhD students and my collaborator Andrea Rocco at Surrey, trying to figure out a way of solving certain equations or trying to find a way of modeling a quantum phenomenon. And we realize we don't know which directions to go in. How do you solve that integral? What sort of approximation can we make there? And there's an excitement in not knowing. That ultimately, that's what keeps me awake at night. I swear the other night I woke up to go to the bathroom, came back to bed, and I'm lying awake, and I start thinking about this equation that one of my students has sent me, and I'm thinking, okay, and I'm I've got Greek symbols floating around in my head and calculus in my head, in my half asleep, and I figured something out, and I didn't jump up and scribble it down, no, because my wife wouldn't have been pleased about that, putting the bedside light on. But the next morning, I oh yeah, I can do that, right? So for me, that's the wonder of what I do, that it's the thing that I want to figure out lying in bed. It's the last thing I think about before I go to sleep, first thing I think about in the morning. Not every day. I'm not that sad. But, that excitement of the mysteries that are yet to be solved.
Well, just as well you didn't solve a mystery in that moment, because it would have been a discovery that you'd have to publicly tell everybody you discovered just after taking a really good midnight urination. So ultimately, most people discover things in the bath, Jim. We can say that you were in the bathroom.
Similar.
A similar sort of thing. But ultimately, where does that leave us? What do we know that we don't know? And how do you know that we might eventually know what might seem unknowable? Now, I don't know if that made sense.
The known knowns, the known unknowns, and the unknown. Yeah. We know there are mysteries out there that, there are phenomena that we need to somehow explain properly. The nature of dark matter, invisible stuff out there in the universe that's holding galaxies together. We know it's out there. We know it has a gravitational pull. We don't know what it's made of. We know the universe is expanding ever more rapidly. So we know there's something called dark energy. We don't quite understand its nature. We know that when just after the Big Bang, matter and antimatter would have been created in equal amount. But we don't know why there's no antimatter around now. Most of the universe, thankfully, is normal matter. We don't understand how to unify quantum mechanics with relativity. There are other examples. We don't understand, for example, what is the correct explanation of quantum mechanics. How can a particle be in two places at once? How can Schrodinger's cat be dead and alive at the same time inside the box? So these are things we know that need to be resolved. Of course, we don't know what surprises there might be around the corner, new phenomena to be discovered. The dark energy, when it was discovered back in 1998, was an absolute shocking surprise. No one anticipated. We thought the universe was expanding, but the expansion rate was slowing down, that gravity was putting the brakes of, all the matter and energy in the universe was stopping it from expanding so rapidly, slowing it down. We thought, well, maybe one day it'll recollapse in on itself in a big crunch. But no one anticipated there was something that was winning the battle against gravity and making the universe expand ever more quickly. So that's part of the excitement, that you really don't know how much we don't know.
Well, no, despite the fact that we don't know some things, we can actually apply what we do know to the creation of new technologies. And our understanding of space and time, for example, that's led to so many technological innovations, hasn't it?
Oh, absolutely. I mean, I think that what I don't want to give the impression of is that somehow we're floundering, that we don't understand anything about the nature of the world. We pretty much understand all the phenomena and all the mechanisms, all the stuff that goes on around us in our world. When I talk about what we don't understand, that's very on the far edge of existence. That doesn't really impact our daily lives. But Einstein's theory of relativity that explained the nature of space and time tells us that gravity slows time down. So time itself runs slower the stronger the force of gravity. You think, well, come on, that's just some guy with wild hair comes up with this thing. Great for sci-fi movies, but not in the real world. But then that's how your smartphone works. That's how GPS works, because GPS and your phone relies on signals coming from satellites or in orbit around the Earth that triangulate and pinpoint your position. Because those satellites are orbiting the Earth, they're feeling weaker gravity than we are on the surface of the Earth. And so their time literally runs at a faster rate on the satellite than it does on Earth. So we have to deliberately slow the clocks down on board the computers on the satellites so they match the rate of clocks ticking by on Earth in order to get GPS working. So there's Einstein's theory of relativity about time slowing down, which leads to time travel and all sorts of wonderful explanations. But without it, technology that we take for granted just simply wouldn't work. We'd be lost.
We can go one step further now, because physics isn't just being applied to technologies that are purely based on physics theories. They're being used in interdisciplinary research. So we're starting to see physics informing research in biology and things like chemistry. Could you give us some examples of that?
Yes, it's always been true that, are the boundaries between although we learn physics, chemistry, biology as separate subjects at school, once you get into, the cutting edge of research and developing technologies, it's always been true that you have this multidisciplinary approach. And what we're seeing in the 21st century is the most exciting areas, developments in technology, whether it's genetic engineering, whether it's robotics and artificial intelligence, whether it's nanotechnology, they require input from lots of different fields. And one area in particular that I'm interested in my research is the application of quantum physics in molecular biology. So this is this new area called quantum biology, which is still speculative. And it's built around the idea that there are certain mechanisms and phenomena inside living cells which seem to only be explainable by appealing to the laws of quantum mechanics in a very strange way that I think a lot of scientists still find they're very skeptical about it. And it is speculative. But for me, it's wonderfully exciting to think that maybe the mechanisms of life itself rely on these counterintuitive ideas in the quantum world. Without quantum mechanics, life has had 4 billion years, and during that time, evolution has reached down into the quantum world and plucked out some tricks that allow it to work more efficiently. I mean, so that's still early days yet, but very exciting new field.
So it could eventually be possible that quantum mechanics and quantum theories can explain the emergence of life itself.
It's very easy to appeal to quantum mechanics to say all mysteries we don't understand. Well, that's quantum mechanics. Quantum mechanics explains consciousness or explains, heaven forbid, nonsense things like homeopathy or whatever. And so, because quantum mechanics has this mystical, mysterious appeal to it, it's tempting to use it to explain other things we don't understand. So I wouldn't go so far as to say quantum mechanics might explain the origin of life or the nature of life itself. But, who knows? It's exciting to think that quantum mechanics might play a role in an area where we were least expecting it, inside living cells.
It's so interesting what you say about that, because people do get carried away by the idea of quantum, and suddenly quantum can explain everything, and we have things like quantum woo, and if I think things, the universe will align itself to give me what I so desire. There's been such a misunderstanding in many ways of physics, and you try and deal with some of that in the book by looking at this word truth. In fact, the word truth features throughout the book, and you really look closely at how science deals with this tricky issue of what is true, what is consensus, and what is dogma. Why do we have to be so careful when we talk about truth?
We're seeing the importance of understanding how science works more than ever. When politicians say we are following the science, or we're appealing to the scientific evidence, or science tells us this, people really need to understand how science works. The idea of reaching consensus, the idea of coming up with a hypothesis that is makes predictions that are repeatable, that can be tested experimentally. It really is very worrying when you see on social media the proliferation of conspiracy theories. People who promote them seem to think they are behaving and thinking scientifically, but they're not. Because, in science, if you're faced with evidence contrary to your hypothesis or your theory, you have to revise your understanding in the light of that new evidence. In so many ways, when people appeal to science in a very loose way to develop whatever theory or dogma or ideology they want to promote, they're not following the scientific method properly. Yes, scientists have their own vested interests. I want to get my research grant, or if I'm a string theorist, I want to believe that string theory is the correct theory of everything, and I want people to give me research money and students so we can carry on doing that. But broadly, the scientific process itself does evolve by consensus. If I come up with an idea, someone or carry out a measurement and discover something, and someone else has to confirm it, it has to be reproduced. So there are lots of fail-safes built into science. But ultimately, I still think there is that single objective reality, that truth out there, the way the world actually is. And science, the scientific method, is the most reliable way of getting as close as we possibly can to that truth.
I mean, in this day and age, people seem to have their own truths about how the world works, and you've mentioned conspiracy theory there. So how do we do better? How do we filter what is real science and what is pseudoscience, especially in an age of things like Twitter?
It is really hard when there's so much, you're bombarded left, right, and center by so many YouTube videos and views and opinions that go viral, and there's all this confirmation bias, and we live in these filter bubbles that where we are fed the stuff that we want to believe in, and therefore we believe it. I'm not sure what the answer is. I could glibly say, well, not only should we communicate the scientific ideas, talk about the Big Bang or quantum mechanics, we should also explain how science works. But I think it's true. I think teaching certainly, kids at school the scientific method. What does it mean to have a theory? A scientific theory is not the same as I have a theory that aliens visited me last night. A scientific theory has to satisfy certain criteria and strict rules and regulations. So I do think explaining to people how the scientific process works and be open-minded, that if you believe something to be true, don't believe it with certainty. Use doubts and self-criticism. Think about whether or not that could be wrong. Listen to evidence from an opposing view and see if that makes sense. People think scientists are closed-minded. No, quite the opposite. With in the hope that we wouldn't discover the Higgs boson, we want to hammer and kill our theories. We want to replace them with better ones if we can. We don't want to maintain the status quo. So just be open-minded, but not so open-minded that your brain falls out. That's the only worry I have.
Well, it was interesting to see in the book that you said that doubt and not trusting your senses and ignoring common sense can sometimes be the things that actually make good physicists good physicists. And in many ways, those sorts of things are key to the progression of science. Is that right?
Having doubts, yes. I may have said at the beginning that one of the reasons I fell in love with physics, that it was basically, I saw it as puzzle solving and common sense. It is the way the world works seems to make sense. It's explicable, it's understandable. And yet there's a danger in assuming that, well, it's just common sense that that's the way that works. Because very often, if we don't apply the scientific method, we can be led to the wrong conclusions. And science stops us from using what we think is common sense in coming to a conclusion about something or the way something works or an explanation. Sometimes the scientific method says, no, what you expected to see, what you thought was logical, actually isn't the way the world is. And so always having doubt, always having the willingness to revise your worldview in the light of new evidence is the only way we make progress in science. We have to make mistakes. Otherwise, we'd never change our minds.
Well, in a funny sort of way, then, do you think that post-truth is actually the key to the history of science? In other words, if it wasn't for the seekers and the searchers inventing new ideas and suggesting new truths, then perhaps we wouldn't have some of the physics theories that we have today. For example, some claim the existence of parallel universes just to make their science work today, and it may be proven to be true and it may be proven to be not true, but we need people using the tools of post-truth to challenge the scientific dogma of today for science to progress, don't you think?
Yes, but science only progresses when those ideas can be tested. It's true that postulating the existence of a multiverse and an infinite number of parallel universes is really no different from theology, or sort of abstract philosophy. Because you could say anything. If you can't test it, I can come up with any idea. There's a difference, though, between some of these highly abstract, esoteric ideas in fundamental physics, like string theory, like multiverse theory. There's a difference between them and other sort of post-truth ideologies or woo-woo, as we might say, because they are built on a foundation of trying to explain the world that we know. The parallel universes does explain stuff. It will be great if it turns out that parallel universes really do exist, because that would explain why our universe is so special. How come all the dials for everything in our universe are tweets and tuned in just right to allow us humans to exist and have this conversation? But wanting something to be true because it's a neat idea isn't science. Science is only when that neat idea gets tested and verified and it makes predictions that turn out to be better than any other theory can predict.
So in other words, there's really a difference between scientific theories and scientific opinion.
Yes, yeah. I mean, scientists are humans, and so they will have opinions and ideologies and views and dogmas like anyone else. But a scientific theory that has been tested against experiment, against observation, is something that transcends human fallibility and opinion and views and ideologies because it stands the test of the scientific method.
Listening to you, Jim, it sounds like I'm listening to a physicist, obviously, by training, but also there's so much in what you say that makes me feel like you have a little bit of a philosopher in you. And do you think there's a relationship between physics and philosophy? Do you think philosophers have added to the world of physics? And do you think philosophers and physicists, they could become uncomfortable bedfellows? Or are some physicists actually deep down secret philosophers?
Philosophy and physics, I think, have always been actually not too uncomfortable bedfellows. If you think back to some of those heroes of physics that I'd love reading about, certainly as a student, Einstein and Bohr and Feynman and others, they were steeped in philosophical thinking. They acknowledged the importance of philosophy in helping a science like physics move forward. So I don't think science and physics in particular can advance without the clarity that's brought to new ideas from philosophers. People often talk about philosophy is there to help ask the right questions, and science then attempts to find the answers to those questions. And I think that's true. And it frustrates me when colleagues would say that philosophy is dead, that there's no room for philosophers. We don't need them anymore. Fundamental physics has taken over their role, and we can do very well without them. I think we're getting to the point now where there are these mysteries about the universe that we don't understand. I think we do need the help of philosophers to sit down and talk to us and try and maybe give us a different angle, a different way of thinking about solving some of these problems.
Now, we have one of our first questions from YouTube, and it's from Dave Weaver, who asks, will traveling in person beyond this solar system ever be physically possible?
Oh, since he's put the word ever in, then absolutely. It won't be in our lifetime. But there's absolutely no reason why we couldn't imagine the technology. Nothing in the laws of physics would stop us doing it, of course. It's just the technology. Having the technology, the propulsion system that would allow us to travel that distance is absolutely possible in science fiction. The very good science fiction has really shown how that might be possible. You travel at a significant fraction of the speed of light, and Einstein's relativity says that your time will slow down relative to the universe outside. And so what might to us left on Earth seem to be a journey that takes many, many decades on board a spacecraft traveling at a fraction of the speed of light, it would be a lot shorter. So you could actually get from one side of the universe to the other in half an hour, provided you nudged close to the speed of light. Just don't bother trying to come back again and tell your family all about it, because a lot more time would have gone by on Earth.
And you might accidentally end up behind your daughter's bookcase if...
that sort of thing, exactly.
That sort of thing might happen. Do you actually think that our physical human bodies will be able to travel to outer space, or do you think it might just be our minds? In other words, if we can get information to travel at the speed of light, what we may do is send a robot in advance of us and sit here on planet Earth and control that robot as an avatar version of ourselves on another planet or on another spacecraft. Do you think it's more likely that our minds will travel to space rather than our bodies?
I think if we look into the far distant future, then that's absolutely very likely. But of course, the one thing we can't do is break the laws of physics and send any information faster than the speed of light. So even having that robot reaching Proxima Centauri, the closest star system to us, just 4 light years away, it takes 4 years for us to send our instructions through to the robot there, and 4 years for it to come back again. So whatever technology we develop, we still aren't, as far as we know, able to break that light speed barrier, despite what Star Trek might tell us.
Oh, if Star Trek was true. So we have a question from Lisa on YouTube who asks, will an understanding of dark matter expand our understanding of gravity?
I'm not sure that it would. I mean, the fact is dark matter behaves gravitationally like normal matter. It's stuff. It just happens to be made of particles that don't interact via the electromagnetic force. So that's why it seems invisible to us. So the challenge is really not so much of understanding how dark matter behaves gravitationally, but what it's actually made of. But then, again, with this idea of having doubts and never being certain about things, we don't know if dark matter behaves in the same gravitational way that normal matter does, exactly the same way. And if so, does it mean we have to revise Einstein's general theory of relativity, the way matter curves space-time? Does dark matter do something different? There are ideas that maybe dark matter doesn't even exist at all, that maybe we just have to revise our picture of what gravity is to explain away what we see as dark matter. The evidence for its real existence is too overwhelming at the moment. But yeah, who knows? It might revise our picture of gravity.
We spoke a little bit about some of the applications of some of the new physics like quantum mechanics, and Ben Greenaway asks, how far do you think we are from a home or personal quantum computer? Of course, Google has achieved quantum supremacy, whatever that means, but in terms of having one of these quantum computers in our homes, how far do you think we might be?
Probably closer than we thought we would be 10, 20 years ago. Last year, I published my first novel, science fiction thriller, Sunfall, which is set 20 years from now, in 2041. And in it, one of the protagonists, a young cyber hacker, uses a quantum computer, a home quantum computer, to hack into some sort of highly encrypted secret information, which then sort of kickstart the whole adventure. So I do think maybe 20 years from now we will have fully working quantum computers, because, as I say, companies like Google and IBM and others are working very rapidly. Quantum supremacy may not actually mean we've built a proper quantum computer, but it's a big step along the way, and we're seeing success happening quite regularly now.
It seems like everybody wants you to make predictions, but I guess this is the Futures podcast. We have another question from YouTube from Susie, who asks, from your perspective on the current scene in physics, when do you think the next scientific revolution might arrive?
My hunch, and what do I know? My hunch is that, when we talk about wanting the next Einstein or the next Hawking to come along, I think the problem in really sort of revolutionizing fundamental physics is getting to be so complicated that it may well be an AI algorithm that's going to help us do that. A good friend of mine, a guy called Demis Hassabis, who is CEO of DeepMind, probably the world's leading AI research company, I agree with him. He says that maybe we've come as far as we can with our crude monkey brains, and we need an AI to really solve these deep problems, finding the patterns in the mathematics that are far too complex for humans to see. So the next revolution may well be 20, 30 years from now, but it may not be a human that actually takes us forward.
What you're doing here is such a wonderful example of the public communication of science. And why do you think it's so important that we make this sort of work accessible to as many people as possible? Why is science communication so important to you, Jim?
A number of reasons. One is that, I've always, ever since I started communicating science, talking to the public, writing sort of articles, talking to journalists. I mean, this goes back over 25 years ago now, when I first sort of ventured out of my ivory tower of academia. I'd always felt that I wanted science to be part of popular culture, that we would talk about black holes and dark matter and quarks and whatever down the pub, in the restaurant, among friends, in the same way that we talk about music and sport and politics. So for it to be just part of the conversation, and I think to a large extent that has happened. People know about the Higgs boson, they know about the discovery of exoplanets, and they know about gravitational waves and so on. So I think just because in the same way that we appreciate art and music, there's no reason why we couldn't appreciate, even though we don't have the deep mathematical understanding, we can't appreciate some of these concepts in science. That's one reason. Another, of course, is to inspire the next generation. That's always going to be true. We need more scientists and engineers in an increasingly technological world. But the third reason is one that we are now seeing unfold today. People are faced and bombarded with conflicting evidence about the coronavirus, about how it's spreading, whether we should wear face masks, whether we should social distance, do I go back to work? Is it coming down? Is there going to be another spike? There are so many questions we want to know. And everyone is told all the time that the decisions governments are making are based on scientific evidence. And so it's vitally important that people understand how science works, that it is not always about having all the answers to begin with. We have to be honest and transparent and say, well, to the best of our understanding, this is what we think is happening. But maybe next week we'll find some more out and we'll realize that we weren't quite right. And it's not a failing. It's not that, right, sack them all, sack all the scientists. What do they know? They were wrong. They said something last week. They said something different this week. They know nothing. That's why we have to explain how science communicates science and how it works and the scientific method itself.
Sometimes do you think there's actually a danger that comes from increased public interest in science? For example, the Schrödinger cat experiment originally was supposed to make people think the whole thing couldn't be correct, but it entered the public consciousness, and with things like quantum, we now have quantum woo and our thoughts can affect the universe and all of these ideas that get misconstrued because the public thinks they understand something about the science, but in actual fact, it's the way in which the science is being communicated, which is the issue, really.
There's certainly a danger that, people know a little bit of science and they assume that means they are experts. And my view is as valid as yours, just because you've got a PhD and you've spent, I get regularly very sweet emails and tweets from people saying, I know nothing about science. I'm not educated in physics at all. However, I've figured out what dark matter and dark energy are, and it explains the Higgs boson and explains this. And you think, yeah, but I've spent my whole life working hard trying to understand this stuff, and you just say, well, I've got no background, but I've just come up with this idea. But so I think it is dangerous for people to know a little bit based on sort of popular accounts of science, and then just completely get the wrong end of the stick. But on the other hand, it's great that people are curious. It's great that people are thinking about this stuff. When the LHC was first switched on, people were worried that it was going to create a black hole that's going to swallow up the whole Earth. Of course, that was nonsense, but it got people talking about particle physics and quarks and so on. And so I think part of the conversation is fine, provided it doesn't then infect and create, conspiracy theories and people going around sort of burning 5G masks and saying, 5G is creating viruses. So I think there's a danger in people having a little bit of scientific knowledge and extrapolating it into Crazyville.
We on that note, we have another question from YouTube, this time from Ingrid, who asks, are there parallel or other ways to explain phenomena of reality besides mathematical language? For example, analogy or metaphor, diagrams or drawings. Could these actually be cleaner and better than mathematical language in many ways? Or is maths always going to be the paragon through which we describe physics?
Ultimately, the universe speaks in the language of mathematics. So ultimately, that is the way, we have to understand reality. But in other ways, I think she's right that there, metaphors and imagery can be very powerful. A lovely example is the great American physicist Richard Feynman, who developed what are called Feynman Diagrams, which are ways of describing how subatomic particles interact and create new particles, and E equals mc squared. It wasn't rigorous mathematically, but it was a very powerful way that gave new insights. So I think there are lots of ways that allow us to understand better, maybe understand the mathematics better, or give us a picture of reality that allows us to move forward. So yeah, all those tools should be available to us.
Well, we have another question from Andre, who asks, what do you think the confirmation of Bell's theorem through experiments tell us about the nature of the universe?
John Bell was an Irish physicist who essentially helped bring to a head a long-running debate in physics. Very often in popular accounts, it boils down to an argument between the two biggest names in physics, certainly in the first half of the 20th century, Albert Einstein and Niels Bohr, the Danish father of quantum mechanics. Each of them had a different view of what quantum mechanics meant. And what John Bell did was come up with a theory that said, you can't both be right. If this condition is satisfied, he's right. If this condition is satisfied, he's right. And so Bell's theory, or also known as Bell's inequality, was then tested experimentally. And it gave us a way of really probing the mystery of the quantum world. It's not the end of the story, though. It hasn't resolved things yet. So we still argue about whether Einstein was right or Bohr was right. What is the ultimately correct description of quantum mechanics? We still don't know. That's one of the outstanding mysteries. It's probably the thing that I most want to have resolved in my lifetime. But John Bell's certainly a big hero of mine. I met him a couple of times. If he says something, I sit up and listen, because I think he's one of the great unsung geniuses of physics.
You mentioned briefly your work in science fiction, and science fiction is so important for how we perceive the world of science. And I guess that this is more of just a personal question than I have for you, but where have you seen physics principles best represented in science fiction? And also, where have you seen some of the worst case examples of physics represented in science fiction?
I give a regular schools talk to teenagers on time travel and separating science fact from science fiction. And so I think when it comes to good science fiction with time travel, that's a really nice example. Probably the best movies on time travel are Interstellar. I mean, despite Matthew McConaughey floating behind the bookcase in his daughter's bedroom bits towards the end, which gets a bit trippy at the end of the film, but Interstellar, however weird or wacky you think it is built on solid physics. There's nothing in Interstellar that violates the laws of physics, and that's thanks to Kip Thorne, one of the Nobel Prize-winning physicists, American physicist, who was one of the producers on the film, and he made sure the science was right. At the other end of the scale, I don't know, hot tub time machine. There's a pretty awful example of time travel. So yes, I mean, there's a whole range. There's science fiction that is really well made in movies or well told, particularly if scientists are involved. So the best science fiction is probably from the classics of people like Arthur C. Clarke or Isaac Asimov. Why? Because they were scientists themselves. And the worst science fiction is the fantasy, which is not really meant to follow the rigors of science. But that's fun in its own way. I love watching the Marvel movies. I don't storm out of the cinema because Spider-Man's broken the laws of physics. I just enjoy it.
Another part of that question is what made you and inspired you to write science fiction? Why did you suddenly realize, instead of writing these non-fiction tomes and explaining science, perhaps the best way to do it is through the use of science fiction?
I'll be honest with you, it wasn't altruistic in that sense at all. Like my publishers, I just published a book and it was at the launch party. Actually a book on quantum biology, this new area that I talked about earlier. And the publishers wanted to know what my next book was. And I said, well, I've sort of got everything off my chest that I wanted to write about, written about relativity and quantum mechanics and so on. Maybe I'll write a novel. And I just said it as a joke. And they said, oh, really? What would it be about? I said, I don't know, probably science fiction. I enjoyed sci-fi, Michael Crichton. I said it would probably be a thriller because, I love, Stephen King books. Before I knew it, they set me up with a science fiction commissioning editor, and I had to come up with an idea. But of course, once that seed was planted in my head that, Jim, maybe you should write a novel, that was it. Then that was that was what I was sort of thinking about last thing at night, first thing in the morning. And it was a real, a steep learning curve, but an absolutely fantastic experience.
I mean, how does the process change from writing something like the book that we have here to something that's a science fiction book? Does it change the way you have to write? Does it change the way you have to think?
Very much so. It was very liberating in a way, but also, I know how to write nonfiction. I know how to explain. That's what I spend my life doing. I explain. But in fiction, I have to invent a whole universe. I have to invent a world and invent people who didn't exist before my brain thought them up. And suddenly they have to be people that you can believe in, and they have to be three-dimensional. They have to have personalities. So I couldn't, come home from work or be in my office and think, oh, okay, I've got an hour before the next meeting, I might get another chapter down of my novel. No, I had to shut myself away. Actually, in this study here where I'm recording this evening, and I block off days on end. I wouldn't stay in the study for days on end, but block off days where I wouldn't check email, I wouldn't deal with any other work, and just immerse myself in building this imaginary world. And it was very, very different from writing nonfiction, apart from all the creative writing techniques that you have to learn, show, don't tell, mind your point of view, and all the stuff that hadn't occurred to me. I remember starting one paragraph in my novel with nevertheless, and my editor came back to me and she scratched out. He said, don't use the word nevertheless in any novel you ever write. That word is barred from fiction. Oh, okay. No one told me that.
I was surprised by so much in the book, and you're so matter-of-fact about the way in which physics has evolved and changed throughout history. And I was personally surprised, but it made me wonder, is there anything that still surprises Jim? It feels like he knows it all. So perhaps there's no new surprises for you. Is there anything recently that's made you gone, oh, wow, I didn't even think about that?
Yes, I think it happens regularly. That's what makes physics research so exciting, that I'm constantly appreciating how little I know. I think, when you're doing research and particularly when you move into a field maybe that you haven't worked in before, as I've been doing the last 2 or 3 years, an area called open quantum systems, the nature of how a quantum object interacts with its surroundings, concepts that, are bandied about now in popular science, decoherence, quantum entanglement. And you realize there are people who've been working in this field for years and years and years and know so much more than you, that I'm constantly surprised when I learn something new and I think, oh, I really have to remember that. And of course, now I'm getting to the age where I don't remember stuff. so I read it again a month later and I'm surprised all over again because I've forgotten it from the first time.
We have one last question, I guess, from YouTube, which is, do you think there's a limitation to what we can understand because of our human consciousness? In other words, do you think there's some fundamental limit to what we can understand with mathematics and metaphors purely because we have this wetware human brain?
It may be the case that our brains are not complex enough to unravel the deepest level of reality, or the truth of objective reality, which is why I said it'll take an AI to help us achieve that. But we've come this far, and we haven't reached any limit yet. Our brains are three-dimensional, and yet we can imagine 4, 5, an infinite number of dimensions, because we have tricks, because we have mathematics. So developing mathematical tools allow us to go beyond the confines of the images that we can create in our brains. We haven't reached that limit yet. That's not to say that however long the journey is to uncover the deepest secrets of the universe, our brains are capable of doing it. It maybe we will start reaching a stumbling block where you think, no, that's it. Can't get my head around this anymore. This is as far as we can understand. But we haven't got there yet, so I remain optimistic.
I mean, you've teased it a couple of times now, but you say in the book many times that physics is waiting for the next Einstein to come along, but perhaps the next Einstein will be an artificial intelligence, perhaps an AI Stein, if that makes sense. And Susie goes one step further and says, to understand that AI, well, we have to actually augment not just our understanding of physics, but augment ourselves. How will we be able to realize if an AI made some revolutionary scientific discovery, if again we had this limitation of our own consciousness and our own understanding?
I think in that case, we're going to have to rely on the AI to explain to us, as we would explain to a toddler. We are not going to be able to appreciate what the AI is doing or how the AI has come to the conclusions it has. We're already seeing this, famously, these AI algorithms developed by DeepMind, like AlphaGo and AlphaZero. These are the algorithms that learn how to play chess or the Chinese game of Go just by being given the rules of the game. And then they play against themselves 1,000 times, and then they can beat any human on the planet. How they do it is almost a mystery, we because it's gone beyond what we can figure out. That's the whole point of these ideas of machine learning, that it's learning itself. We're not programming the computer and saying, right, if this, do that. I'm giving you the instructions, therefore I know as the coder exactly how you're going to behave. True AI, when it comes, is going to be soaring off, solving problems without us ever understanding how it does it. So it's going to have to be quite gentle and explain in simple language to us mere mortals exactly how it's done what it does.
I love the idea that we have to train our AI to be good science communicators before
Absolutely.
they're good scientists. That thing about scientific discovery and curiosity, and reading your work and listening to you, it feels like that is really at the heart of what it means to be human. And do you think there's a relationship between our desire for discovery and our desire to know these massive questions? Do you think that just goes back to the very heart of what it means to be human, our own humanity?
Absolutely. No, absolutely. I think that's what defines our human. We talk about what it is to be human, to know our place in the universe. There are traits that we have to do with, empathy and compassion and kindness that I think is a wonderful sort of ways that we behave towards each other. But also we've always had this curiosity about the world. It's built into our DNA. It was probably an evolutionary trait. You want to know what's behind the next hill. You want to know if there's a saber-toothed tiger hiding behind that tree. Trying to understand the heavens and therefore the seasons and to make our lives more comfortable. We've always wanted to know our place in the universe. So I think we'll never stop asking those questions. We are born curious. All children are by their nature curious. Why is this? Why is that? But why? Most people grow up and stop asking why. A scientist is just a child who's never grown up, has never stopped being curious.
So on that note, Jim Al-Khalili, thank you for joining us today.
My pleasure. It's been fantastic.
Thank you to Jim for sharing his insights into the fascinating field of theoretical physics. You can find out more by purchasing Jim's new book, The World According to Physics, available now. And don't forget, you can watch the full unedited video of this conversation at futurespodcast.net, where you can also find out about all of our upcoming live stream events. If you like what you've heard, then you can subscribe for our latest episode, or follow us on Twitter, Facebook, or Instagram at FuturesPodcast. More episodes, transcripts, and show notes can be found at futurespodcast.net. Thank you for listening to the Futures Podcast.